Welcome to video 2 for the rotation unit. In this one we're going to talk about something new, radial acceleration. I want you to think about a particle going through uniform circular motion, so it's going in a circle at a constant angular velocity. The magnitude of the velocity vector would remain constant. So let's think about this. So I got something that's spinning, and it's spinning at a nice constant angular velocity. So if I were to take a look at that particle as it goes from here to up here, we would have this tangential velocity here and here. It's going through an angular displacement. We even have the relationship V equals R times omega to relate those two. So if omega is constant and radius is constant, then velocity should be constant. So this particle is moving at a constant angular velocity, which means that the magnitude of the velocity is the same. So if the velocity here is 1 meter per second, the velocity up here would be 1 meter per second. However, translational or linear velocity is a vector. That means it has magnitude and direction. So the speed or the magnitude may be constant, but the direction is constantly changing. So at first it was, initially it's pointing up, and then finally it's pointing to the left. And you can tell that that direction will constantly be changing. So at any instant in time, the direction of the instantaneous velocity is tangent to the path. So that means it's going to be different every single time. So since velocity is a vector, it has direction. Since the direction is changing, that means the velocity is changing. So even though it is not slowing down or speeding up, there is still an acceleration. So imagine that, an acceleration that does not require the object to either slow down or speed up. We call this type of acceleration radial acceleration. Radial coming from the fact that it's originating from an object going in circular motion. Let's derive it. Let's create an equation that helps us calculate this radial acceleration. First off, let's take a look at an object going between 2 points, A and B. I'm going to go slightly into calculus. I'm going to call this a delta theta. I know that at point A, the velocity has an initial velocity, and at point B, it has a final velocity. Now, as A gets closer and closer to B, so imagine those 2 points getting closer and closer and closer, the arc length, S, stops looking like a curve, and it starts to look more and more like a straight line, a delta x. So imagine points A and B getting closer and closer and closer until S starts to look like a straight line. All right, so let's go ahead and get some math down here. Velocity equals delta x over delta t. So I can rewrite this and I can say that delta x equals velocity times delta t. The next thing I can do is I can take advantage of the fact that arc length equals radius times theta. Remember, theta is arc length divided by radius. So in other words, I want you to see that S becomes delta x equals r times my delta theta. So I'm going to take this formula and this one, I'm going to put them together. And once I've done that, I'm going to solve this for delta theta. I'm going to call that equation 1. Okay. Next thing I'm going to do is I'm going to take a look at delta v. That's going to be final velocity minus initial velocity. They're all vectors. So another way of looking at this is I can say the velocity, final velocity equals the initial velocity plus my delta v. So when I put vectors head to tail, what this would look like, if I were to redraw this, I'd have my initial velocity, I'd have my delta v, final velocity. So notice how I used head to tail there when I add two vectors. And whenever I subtract two vectors, I put them tail to tail. What that does is it allows me to make a second circle. In this second circle, the radius is now going to be that initial velocity. I'm going to put my final velocity. Remember, when you subtract two vectors, you put them tail to tail. And then this right here is going to be my delta v. Now, looking at the geometries here, this angle between these two will still be delta theta. That just comes from geometry proofs and everything else. So remember that theta equals arc length over r. So looking at this time, I have my delta theta. My arc length is going to be delta v, and my radius is going to be v. Now, why did I choose v and not v naught? Well, it doesn't matter. Their magnitudes are the same. If v naught is 10 meters per second, v is 10 meters per second. It's not their magnitude that's changing, it's the direction that's changing. All right, so I'm going to take a look at this. This is going to be my equation 2. Now I'm going to put equations 1 and 2 together because notice that they are both equal to delta theta. So when I do that, I have that right there. I'm going to cross multiply. And then I'm going to divide the r over and the delta t over. And I hope that you recognize this delta v over delta t as acceleration. So my radial acceleration equals velocity squared, the magnitude, velocity squared, divided by the radius of the circle. So that is the formula for radial acceleration. Don't forget, our other bridge equation was v equals r times omega. So radial acceleration can also equal r times omega squared. So I'll let you think about the algebra for that. And it just comes from the fact that v equals r times omega. Okay, once we have a radial acceleration, we can begin applying Newton's second law. So here's a little bit of review. We know that the magnitude and direction of the acceleration of any object in circular motion We can use its mass to apply Newton's second law to solve problems like orbits and cars going around circles. So remember that Newton's second law said that the net force equals mass times acceleration. So what I can say is that the radial force equals mass times the radial acceleration. So that gives me two possibilities. I just plugged in the formula for radial acceleration. So we call this a radial force. And the radial force really is just an idea. Something has to provide the radial force. So tension, gravity, friction, elastic something. All objects want to maintain a straight line path from their inertia. Circular motion, you have to recognize, is unnatural. Nothing wants to go in circular motion. Therefore, there must be an outside force that's present to force the object into circular motion. That outside force then is what we call the radial force. Without radial force, no object would be able to make a turn. So we'll finish up this video with a quick little example here. Let's say I have a car that wishes to go in a circular path. Looking at this car, this is like a head-on view. If I were to do like a bird's eye view, this would be like the top of the car. And this car wishes to travel in a straight line path. So there must be some sort of radial force that is directed towards the center of that circle that is forcing the car to make a turn. Some other forces acting on this car would be like a normal force from the ground, a gravitational force, and really that's it. That's the only forces acting on this car. So radial force is an idea. Something must be providing it. Well, if you think about it, friction is providing the radial force, specifically static friction. Now that seems kind of weird. Static friction is stationary, but the car is moving. And the truth is, the bottom of the car's tires, the very, very, very point that touches the earth, is not moving. It's not sliding. It's stationary. It's rolling. So it is a static friction that is keeping the car on the road. So when I take a look at the sum of forces acting on this car, let's say in the x-axis, I see that there's only one, a radial force. So that equals mass times a radial acceleration. Okay, well, that radial force is being provided by static friction. V over r, where r is kind of like the radius of this gigantic circle. For interstate ramps, the radius of curvature is very, very large. Friction, we calculate that with the coefficient times the normal force. Normal force, if we're on a nice unbanked turn, the normal force is the same as the gravitational force. You know, it's an equilibrium on the y-axis. At this point, notice that mass doesn't matter. So to finish this up, the velocity would equal r times the coefficient times the acceleration due to gravity, all underneath the square root. So this explains why the State Department only uses one caution sign for turns. You know, slow down to 35 miles per hour, or you have to go 25 miles per hour on this exit ramp. They get away with using one sign because mass cancels out. So it doesn't matter if you're driving a semi or a sports car. The saved velocity would be the same for every single object. Mass cancels out. All you have to worry about is the coefficient of friction between the tires and the road, what planet you're on, and how large the radius of curvature is for that turn. There are many, many other examples, but this is kind of the basic math. You know, we're going to look at planetary motion. We're going to look at objects being twirled around on a string. There's a lot of things we could do. All right, this is going to conclude video 2.